Hello, everyone. Hello, Olivier.
Good morning, everyone.
Good morning. So I see that there are already a few people here, so we can probably start. Yes, a few. It's a bit scary. Bright and early. So I hope everyone is well rested and ready for another day of full immersion in the world of Bayesian capture models. So, okay, so probably what do you think, Olivier? We should probably start, yeah? Or maybe I wait for, yeah, because we have many things to go through today again. So
Yeah, go ahead. Go ahead.
Okay, so I'll share my screen. Oops, not this one, not this one, this one. Okay. So yesterday we started to go through together the dead or alive module. So how to estimate survival rates and detection rates using Nimble. We've seen how to code a model with constant and time varying survival and detection probability. So today we're going to see how we can try to explore this temporal variation and relate it to some biological variables of different types. And we'll see different ways that we can do this using Nimble. So I've seen yesterday that there was a few questions about this in the Slack. So I think that some of you will be interested by this. Oops. Okay, so let's embrace heterogeneity. So how we can include temporal covariates that we call, for example, X, T. So this type of covariate would take a different value at each sampling occasion. Imagine something that you would measure every year once during the session to represent some kind of environmental variable in your system. We can specify a model on survival rates or detection rates directly in the Nimble model. So for those of you who are familiar with capture-recapture models, it's exactly the same than it would be in JAGs. I mean, there are some little differences that we will go through, but the idea is the same. We can formulate any model on survival rates or detection rates. Here, it's an example with a linear effect of the covariate xt, but we could also imagine more complicated model, non-linear effects, or including random variables, random effects that we will see how today actually with a little example. But just so you know, so it's the same idea than regression. You can formulate a model within the capture-recapture model on survival or detection rates. So it's very handy. So let's use an example because it's going to be easier to go through this using an example. So let's investigate the effect of water flow on the famous deeper data that we used yesterday already. So deepers were monitored in rivers of the north of France, just for the memory, the recall. And we're going to use here the water flow of this river as a covariate to see whether it can affect whether it's related to survival rates at different time steps. So right back in the code, that's the model that we used yesterday. One of them was constant survival or time-dependent survival and constant detectability. Okay, so if we go back to this code, I'm just going to show you what we need to modify to include the covariates. So Let's go line by line to warm up a bit. So delta was the vector of initial state. Everyone is alive at the first capture. No one is dead. Okay. Then we loop on time occasion from the first one to t-1 because survival rates are estimated in between each time interval. So we have t-1 survival rates. Here, what is in yellow is what is new when we include the effect of the covariates. So logit of survival this time. So yesterday, because we didn't have any specification on survival rates, we didn't use logit of phi. We just used a uniform prior saying that phi, sorry, not phi, oh, so French, phi, the prior on phi was just a uniform distribution between 0 and 1. Today, we want to constrain this model to be estimated on survival rate. So survival rate should be constrained on the in between 0 and 1. And for this, we use the logit transformation. So that's pretty standard for survival model. But do not forget to use the logit link here on survival rate. Okay. And on logit of phi, we can specify the model. So here an intercept beta 1, let's say, plus the effect of water flow. So the slope beta 2 times the covariate that we call flow here. So at each time, at each monitoring session, T, flow will take a different value that we measure an average of water flow every year or every sampling occasion. Okay. And of course, we have to provide priors for these two new parameters, beta 1 and beta 2, intercept and slope. So here we say that beta 1, the prior on beta 1 is a normal distribution with mean 0 and SD, a standard deviation of 1.5. Okay, so we give it a relatively large prior on the standard deviation so that it's non-informative. So, okay, so for these two regression parameters, we give non-informative priors using normal distributions. Okay, for the rest, it's the same than yesterday. So the transition matrix, gamma, which control the transition from one state to the next state the following year. So I'll just go through this quickly so that you remember. So probability of going from state alive at time t to alive at time t+1 is survival probability, phi t, in between these two time intervals. Probability of going from alive to dead is 1 minus phi. So probability of dying at times t, of course. We do not forget to index phi by time because phi will take a different value at each time occasion as a function of water flow. Okay, sorry, I'll go through this transition matrix now. So probability of going from state dead to alive is 0. If you're dead, you stay dead, you remain dead. Here, sorry, if you're dead, you remain instead dead with probability 1. Oops. It's the morning, sorry. Okay. So the prior on detection probability does not change. We keep a uniform distribution between 0 and 1 for a vague prior. Imagine we would like to test an effect of some covariate, for example, the number of people that we had available on the field every year. We would include a model here, like we do for survival here. We could also include a model on logit of p, function of beta 3 for an intercept plus beta 4 times sampling effort with some measure of sampling effort, for example, number of people available on the field at each time occasion. Okay, here for simplicity, we just do it on survival, but it's the same. We could do the same. And in this case, P would also be included in the time loop. Okay, because P is constant here, the observation matrix omega is defined with, actually, I think there is a mistake here. There should not be a T time index in there. Okay, omega is constant, so this is a typo. Forget the T here. We will change this in the slides. So omega should actually be the observation matrix and is not indexed by time. So 1 minus P is the probability of being alive and not detected at time t. P is probability of being alive and detected at time t. For an individual that is dead, he's got a probability 1 of being non-detected and 0 of being detected. Okay, same than yesterday. We already say the word about the priors on the regression coefficient. And now we can write the likelihood as yesterday. For each individual I, first we define the initial states. So at first capture, individual I, we draw a value from the initial state vector, which is delta. And in delta, we specified before that at first capture, everyone was alive with probability 1. Okay. So for the following recapture occasions, after the first one, so the one after the first capture, to the last time sampling occasion t, we specify the state process, so probability of going from one state to another state in between the two time occasions. So using gamma, which is the transition matrix. We do not forget to index gamma by time, but we don't have to index omega by time, okay? Because omega is constant, gamma is time dependent. Remember, survival depends on water flow every year. Okay, so we can run this model using Nimble. We cannot run the model now because we've written the model. Now we need to define all the data and constants that we need in the analysis. So we will do this together in the live demo in a bit. But in the meantime, so we just for you to see what the covariate looks like. So water flow each year, so 91, 92, 93, 94, 95, 96, etc. You can see that the second value of water flow in 1982 is about twice as big as the other ones. Okay, so we see here they're all about 400. I forgot the unit though. Liter per. Oh, sorry, my bad. I forgot that. Anyway, much bigger value on the second year of fieldwork. We standardize this covariate, so that's a good practice. We usually always standardize covariates to avoid some scale issues, especially if you are working with several covariates that are on different scales. Okay, so the unit is written here is actually liters per second for water flow. So to standardize water flow, we subtract its mean and divide it by its standard deviation. Okay, that's a way to have this covariate centered on 0 and with variance in between 0 and 1. Then we define the constants for Nimble. So here the constants are going to be number of individuals, number of time sampling occasions, T, first capture occasion of first capture for each individual, and the covariate that we call flow in the model, which is the standardized water flow measured in the rivers. We can then define the initial values. So we need initial values for states, like yesterday, initial values for P that we draw from a uniform distribution in between 0 and 1. So here we say we draw one value in between 0 and 1 from uniform distribution. And the difference with yesterday is that we do not give an initial value for phi, but for beta, because now phi is a function of, remember, we specified log it of phi equal beta 1 plus beta 2 times flow. So we actually need to give initial values not for phi, but for the regression coefficients beta 1 and beta 2. So for this, we draw two values for from a normal distribution with mean 0 and a large variance. So here, variance of 1, SD, sorry, standard deviation. Okay. Next step, which parameters we want to monitor from the model. So we're interested in survival, phi, detection, and we're also interested in the beta, the regression coefficients, because we might want to draw the regression slope, the regression line with the uncertainty around each of the parameters. Okay, so do not forget to monitor the beta. It can be really useful. Also, if you want to interpret the effect of the covariate, it's good to look at the slope and see whether it's positive, negative, or centered around 0. Okay, so we run this model in Nimble. That's what we're going to do together on the live demo. And then we get the estimates. So here is a graph or plot of the regression coefficients. So beta 1 is the intercept. You can see that the credible interval, so the thick line is the 50% credible interval, and the smaller, thinner line is the 90% credible interval, I think. So you can see that the intercept beta 1 for the effect of river flow on survival is clearly centered on positive value, which doesn't actually tell us something about the effect of the covariate. For this, we have to look at the slope. Okay, that's just the intercept. We look at the parameter beta 2, and we can see that it's centered on negative value around minus 0.2. But the credible interval is the thinner life, so the 90% one is intercepting 0. So strictly speaking, we could conclude that, oh, it's crossing 0, so maybe it's not completely significant. The way we usually interpret the parameters in the Bayesian framework, it's also looking at the where on which values the posterior distribution is centered. So here, most of the values of the posterior are centered on negative values. So still, it's a signal that there is something happening. Okay. So maybe we can discuss this a bit more together, but because it probably depends on the view of some people. But here I would say that it's centered on negative values, so there's a signal that there is an effect of water flow on survival. Okay, so if we now look at the posterior estimates of each survival rates each year, in each year, okay, we can see that phi 1, 3, 4, 5, 6 are about similar around 0.6, but phi2 is much lower, okay, around 0.45 for the median. And if you remember, the second year, the river flow variable was about twice as larger as the other values. And it corresponds to the same year here. So probably this year was a very particular year with major floodings, and it is not so surprising that this value could be very different from the other ones. But what we're looking at here, remember, are the survival rates constrained by the fact that survival is expressed as a function of river flow. We do not allow for any residual variation in survival rates here. Okay, so there is somehow a constraint. If we would compare this value with survival rates estimated from a model with just a time variation, the model that we ran yesterday, the values of survival would be different. Here is really survival as a function of the covariate without any residual time variation in it. So it would be actually interesting to compare with the values of the time-dependent model. Okay, so that's what we just did, okay, expressing survival as a function of a temporal covariate. If, and we can imagine that it happens all the time for us biologists, so if temporal variation is not fully explained by covariates, we can allow for some part of unexplained temporal variability, residual temporal variability, by adding a temporal random effect, for example, or other types of random effects. This is very common, like when we work on wild population, is very, very rare that we're able to measure all important covariates. So most of the time, we can maybe measure one or two covariates that make sense and explain some part of variability in survival rates and maybe detection rate too. But there is still a large part of unexplained heterogeneity, unexplained time variability. So it's very interesting to be able to include some residual variation using random effects. So it's very easy to, well, very easy. It's relatively easy to do in Nimble, using Nimble. So we have this model that we can specify on, let's stick with survival for now. So logit of survival rates, beta 1 plus beta 2, an effect of some covariate, plus epsilon t, which represent the random effect, with epsilon t, this residual variation in survival rates at every year, is gonna be distributed like follow a normal distribution centered on 0, because in average the residual variation is 0, with a certain variance. And it's the variance of the random effects that give us the importance, the relative part of residual variation in the variability in survival rates. Okay. So for the JAGS users among us, there is a little difference compared to JAGS here, and it's actually really nice. Oops, sorry, what am I doing? So if we look at the way to code a temporal random effect in Nimble, there's not the whole model here, just the part where we specify the model on logit of phi. That's what we did just before, the effect of the covariate. Here we just add the epsilon, so the residual variation that is not explained by the covariate. So epsilon is time index, because this value of residual variation is going to be different every year. And then we specify the prior on epsilon, which is a normal distribution with mean 0 and standard deviation equal a certain value that we call SDEPS, okay, standard deviation of epsilon. And that's where it's different from JAGs, because in JAGs, if you remember, for those of you who remember, we have to specify the precision parameter, tau. So it's a bit annoying that we had to use, to specify the prior on tau and monitor tau, instead of directly setting the prior on epsilon on standard deviation here. So here we just, in Nimble, we just have to specify a prior on standard deviation of epsilon. So here we say that it's a uniform distribution in between 0 and 10. We just have to specify large enough value here. So 0 to 10 is quite large for standard deviation, so it should be okay. This is a non-informative prior. Okay, so as you can see, and the rest of the code is exactly the same that we saw before. So quite easy and quick. Okay, so we're also gonna run this together in the live demo so that you can see a bit more how it works. So what we talked about just now was temporal time effects. Okay, so temporal covariates, but what about individual heterogeneity? So a covariate that would take a different value for each individual monitored in the data. Think, for example, of a variable like sex. Okay, each individual has one value, either male or female most of the time, and it does not change during the study time or during the whole life of the individual. So it's a fixed individual covariate, does not vary with time. But there can also be different types of individual covariates that can change through time. So think, for example, of mass or size, if the individual can grow indefinitely. So we're going to use different methods to treat each of these two covariates. So let's see how we would include a fixed individual covariate like sex. For the purpose of the example, we're also going to use wing length on Deeper. It's simulated values for wing length. The rest is real data. And let's assume that wing length is fixed early in the life of the individuals and then does not vary, which happen in many birds. Like the length of the wing is some, we could imagine that it's some index of natal conditions of the individuals or general ability to flight or something like this. Okay, so it could be interesting to look at whether it's related to survival rate, for example. Okay, so if we go back to the data, deeper data, capture histories for each year in column, individual for on each line. Then for a time fixed individual covariate like sex or wing length is just one column with the value of the covariate for each individual. Okay, like I just said, this type of covariate doesn't change at each sampling occasion. So it's just one more column in the data. So how to include a sex effect? Sex covariate usually is just a value, two possible outcomes. We could imagine coding the variable sex, taking the value 0 for a male and 1 for a female, for example. And we could write this model on survival rates on logit of phi, beta 1 for the intercept plus beta 2 for the effect of sex, the slope, times sex E for each individual, which would take the value 0 for male and 1 for female. So using this formulation, survival rate for male would just be equal to beta 1. And survival rate for female would be equal to beta 1 plus beta 2 times sex, which is in this case 1, so beta 1 plus beta 2. Here, beta 1 plus beta 2 times 0 equals beta 1 for male, okay? So that's a way to include the effect of sex in the model using this formulation. So we have beta 1 and beta 2. Then when we back transforms these values, we can go back to survival rates for males and females. So how does it work in practice? This time we do not have phi indexed by time, but by the individual I, okay? Because the covariate doesn't change with time, which means that in the model this time we loop on each individual from 1 to n, the number of individual. We write the model on logit phi with beta 1 plus beta 2 times sex e. So do not sorry. So do not forget to index the covariate sex for each individual in the model specification and also in the transition matrix. So in the transition matrix here, it has to be indexed by individual, so by I, and the same for survival rate. Now, survival rate is individual specific, is indexed by the individual. Okay, so here and here. Then we need to specify priors on regression coefficients. So for beta 1 and beta 2, we say that they're drawn from a normal distribution with mean 0 and standard deviation equal 1.5. So uninformative priors here. The trick here is that we want to keep track of male and female survival when we get our results. So we just have to, for convenience, you don't have to do that. You can monitor beta 1 and beta 2, but it's nice to be able to draw posterior distributions directly for survival of male and female. So what we can add in the model is back transforming the coefficients beta 1 and beta 2 on the inverse logit scale to monitor directly survival of male. So 1 over 1 plus exponential of minus beta 1. That's the inverse logit function, which gives us male survival. And same for females. And as we said before, female survival is going to be beta 1 plus beta 2 on the inverse logit scale. Okay, so this bit here is actually just for convenience, so that in the model output you directly can monitor survival of male and female instead of having to back transform the regression coefficients on the natural scale after you run the model. So now concerning the likelihood part, so we loop over each individual, define the initial states, then we loop on each sampling occasion after the first one. So it's the same than before. What changes here is just that the transition matrix gamma is indexed by the individual. So here, do not forget to index with I. Okay, just the transition matrix, while the observation matrix omega that includes links the observation to the states, it's not indexed by individual. P, we did not set a model on detection rate. Okay, so detection rate hasn't changed. Okay, so I'm just gonna say it quickly one more. We set the model on logit of survival, define priors for regression coefficients. We make sure that we directly can monitor survival of male and females by back transforming the regression coefficients. And we do not forget to index the transition matrix for each individual in the likelihood. Whoops, and that's it. So if we run this model using Nimble, we get the results for the regression coefficients. So beta 1, beta 2. So we see beta 1 mean is 0.29. It's minus 0.09 for beta 2. Detection rate is 0.9, so it's around the same than yesterday. Female survival, so that's what we're really interested in, okay? When we just look at the beta on the logit scale, it doesn't tell us much. It's much nicer to be able to look directly at female survival and male survival. So, okay, 0.55, 0.57, so it's not so different. Let's look at the standard deviation, 0.4, 0.3. We have the credible intervals here, the R hat to give us an idea of convergence, and effective sample size that I could not find a word yesterday. So today I'm a bit more awake. So effective sample size is bigger than 100, is quite good for everyone here. So it seems that our model converged nicely, just looking at the summary. And then we would look at the trace plot to see if the mixing was correct, look at the posterior distribution for each parameter and see if they're nice. Now, apparently everything seems fine, just based on the summary here. Okay, so it seems that sex is not so important for deep survival. Another way that we could have we could include sex, that's easier, I think, that would save some programming lines, is to use nested indexing. So instead of coding sex, the variable sex with 0 and 1, we could instead use 1s and 2. So 1 for male, 2 for female, for example, and we could directly use this index sex within the beta coefficient here. So that's a programming trick just to save us some time so that we don't have to use the logit scale here. So survival of individual I is beta. We actually have two beta. So which one of the two we use? We use sex I. So if for individual I sex equals to 1, then this is going to be beta 1. If for another individual sex is equal to 2, survival of this individual is going to be beta 2. Okay, that's a programming trick so that we don't have to write a logit of phi. We don't have to give a prior to we don't have, sorry, to back transform the beta to get male and female survival. We directly have it if we monitor, the beta. Okay, beta here are not going to be on logit scale because of this trick. Is directly going to give us male survival and female survival. Okay, so here beta is the prior for beta is a uniform between 0 and 1 for beta 1 and for beta 2. Okay, so I usually use this formulation because I'm a lazy programmer and it's quicker to write down and to monitor. I don't like to monitor so many parameters. So if you look at the output here, we just have beta 1 that gives us directly male survival and beta 2 female survival. The values are about the same than with the other model. It's just that we have less parameters to monitor. And convergence is good, effective sample size too, and the values are about the same than before. Okay, so that's two different ways to include a fixed individual covariate, and you can choose the one that you think you prefer. So sex was a categorical variable, so it can take either like one or the other discrete value. But what about a covariate like win length, which is a continuous covariate? You know, it can take any value for each individual. Well, we can do the same. We can specify the model on phi. On this time, we cannot use nested indexing because it doesn't take a discrete value like 1 or 2. Okay, it's a continuous covariate. So we specify the model on logit of survival. Here, we don't have the choice. We have to use the logit link and specify the prior on beta 1 and beta 2. Like before, here we use a non-informative prior, saying that beta 1 and beta 2 follow a normal distribution with mean 0 and a large standard deviation of 1.5. So beta is going to give us the intercept, and beta 2 the slope of the effect of wing length on deeper survival. So if we monitor beta 1 and beta 2 and then plot the predicted survival as a function of wing length, so standardized value. Here it was a simulated value anyway. So we see it's pretty flat. It's just for the example, but here we do not see any relation between estimated survival and wing length. Okay, pretty flat. The confidence interval is so that's the mean or the median prediction with the credible interval around the slope. So yes, that's it for wing length. You may want to test at the same time in the same model an effect of several covariates. We're not gonna go through this together here, but there is on the website near the live demos, there is exercise that you can download too, and you have the exercise with sex and wing length together, so you can try to run this if you want. So now a bit different. What if the covariates vary with individual and also through time? It's a bit different. So think, for example, of age. Okay, that's also in the exercise in the worksheets. So you can try to do this. Actually, you have the code. Yeah, okay, so for age, it's a discrete covariate. So you can use nested indexing like we did for sex, okay? You can code age 1, 2, 3, 4, 5, etc. and say that the beta value is gonna change for each value of the covariate age and for each individual, because each individual are different ages, except if they're all born at the same time, but most of the time we have several cohorts. Now think of body size across life, for example. Contrarily to age, we cannot predict body size the next year if we know body size this year, okay? So if we do not capture an individual a given year, we're gonna have a missing value for body size for this individual, because body size can change every year for every individual. So we cannot really infer with certainty the value of the covariate if the individual is not captured. Whether for age, we can, because if we capture an individual that is age 5, we know that the previous year, even if we missed it, we know for sure he was age 4. So for age, we do not have this issue of missing value of the covariate if the individual is not captured. But for other covariates like body size, covariate that can change with individual and time, we have this additional issue. So it's not so easy to include in the model. The best option, the easier option, would be to discretize the covariate using classes like small versus medium versus large, so that we can treat this covariate as a state, and we can, in the transition matrix, instead of having just alive versus dead state, we would actually have alive and small, alive and medium, alive and large, and estimate the transition of individuals in between each of the states in between each time occasion. This is something we're going to see later today with multi-state models. I don't remember the number of the session. So that's one option. Another option is to assume a model for the covariate. Imagine that you very well know the physiology of one species. You can, you know, growth trajectories for your individuals. So you know that if 1 year the individual was this body weight, you can predict pretty well its body weight the following year. Okay, so this is a way that you can infer missing values in your model. Using you would impute them. So there are different papers that we will provide you the reference at the end of this class, with different statistical techniques to impute the missing values depending on which covariate we're talking about. But that's actually, yeah, that's usually one challenge depending on which covariate we're talking about. It's not so easy to include in the model. Okay, so let's do it together. And I've been a bit long, sorry. So I'm not gonna take too long with the live demo. Let's try and do, for example, the effect of water flow. Yep, let's do it together. So we have loaded the deeper data already. I'm just gonna check this. Yes, we did it yesterday. Okay, so it's in there. Now we define the model for the covariate, the Nimble code, using the function Nimble code. So I call this model HMM, phi flow, and P constant here. So delta for the initial states, then I'll loop on time because river flow just varies with time and not with individual. Define the model on logit of phi index by time as a function of beta 1, beta 2. Okay. Transition matrix gamma is indexed by time and phi is indexed by time. Okay. Now I close the loop on time. P detection rate is constant. We use a vague uniform prior between 0 and 1. Omega observation matrix is not indexed by time because detection rate is constant. And we provide priors for the intercept and the slope using a normal distribution with mean 0 and standard deviation 1.5. Okay. Likelihood, initial states, then gamma transition matrix is indexed by time, and we do not forget that here in the likelihood we have to use j-1 because we have t-1 survival estimates, and omega is not indexed by time. Okay, so our model for river flow looks fine. The covariate water flow, okay. We remove here the 7th value because, yeah, we do. This is also something important, that we have as many values of the covariates as sampling monitoring occasions, but we actually have one more survival estimate than we have sampling occasions. So here we remove the last measure of water flow because we do not estimate survival rates for the last monitoring session. Here was 1987, and the last survival estimate that we are able to estimate is survival in between 1986 and 1987. So we do not need the last water flow value. let's standardize the covariates. Look, okay, so it's a vector with 6 values that are centered around 0. Very well. Then we define the constant, number of individuals, number of sampling occasion, first capture. You remember that we did it yesterday. First capture for each individual, so in which sampling occasion each individual was captured the first time. And we also define the covariate within the constants. Okay, so flow, and that looks good. We have all the constants. Then we define the initial values. So initial value for beta, so value drawn from a normal distribution, initial value for detection rate from a uniform distribution between 0 and 1, and initial states. You remember yesterday we said, okay, let's do the easy way and assume that everyone is alive for the initial states for initial values for the states, Z inis. So it's just a matrix, same size than our data, but with ones everywhere. Okay, we assume at initial states that everyone is alive all the time. No one dies. And which parameters we want to save? Survival, detection, and the regression parameters beta. Okay. And we can now run the Nimble model. Code is in phi-flow-p, provide the constant, I provide the data, the initial values, which parameters I want to monitor, number of iterations, we say 10,000, number of burn-in 5,000, a number of chains 2. Okay, so we can run this model. And now I'm scared it's going to take ages on mine, so I've already run it this morning in case. Just see. Okay. Okay, so I'm not very patient, so I'm going to no, it's going so quick that maybe okay, so I'm going to stop it, but you can actually run it on your computer, but I already run it this morning. So let's do as if it had converged and it's all good. So let's try and plot the regression coefficients. Up. So here I use MCMC plots with the model output, and I want to plot the beta parameters. So that's the intercept and the slope for the effect of river flow that is centered around 0, -0.2. Let's look at the survival for each year. So yes, all survival rates around 0.6 and phi2 much lower than the other ones. Okay, so we could also look at the trace plot. Let me copy and paste the function here. Up. I want to look at the trace plot for survival. Just copy and pasting the function MCMC trace from above so that I have the same options like no PDF, and we say that we want the trace plot for yeah, for example, we can look at the one for phi2. Up. Oops, yes, of course. So I could plot also the prior, but I don't want to do this here. Up. Yeah, I just want to look at the mixing and the posterior density for phi2 here. So the mixing is not so bad. Well, I just use few iterations here. So you see 1,500. So if it was a final analysis, I would probably run this longer to have a nicer mixing and a nicer posterior, because here it's a bit wiggly too. Okay, so it's not too bad. It's okay. It just needs a little more iterations to run a bit longer. Okay, I would like to try run the model. So we could run the model with a random effect here. But actually, I see that it's 10 already. Oh, so I think I don't have the time. But you have the code, so you can actually try it yourself. It's just adding the epsilon here when we define the model on survival, and the prior on, and the epsilon is drawn from a normal distribution with standard deviation S-eps, and we define a prior on the standard deviation of the random effect. Okay, so if you run this model, I've done it already, you can then get an estimate of the regression coefficients, detection, and survival, as well as you have another parameter, which is the standard deviation of the random effects. And here you see that I didn't run it long enough because some effective sample size is quite low for these parameters. So it would actually need to run longer. So if you do run it in using this code, maybe increase a bit the number of iterations for the model with random effects. So sorry, so I've been a bit long this morning, so I'm gonna go back to the class. And if it's okay with the next speaker, maybe I can use 10 more minutes to finish going through the rest. Try to be quick. So the main interest also in using Bayesian stats is that we can actually include some prior information when we have it. So what we did until now is using vague priors, so non-informative priors. So usually for survival, we used either a beta distribution 1, 1 or a uniform between 0 and 1, which is exactly the same thing. Here, for the deeper, we got a median or mean posterior survival estimated to 0.56 with a credible interval between 0.52 and 0.62. So what happens if we would actually not use a non-informative prior, but an informative prior? So use, bring some more information in the model. Oops, sorry. So that's the prior that we used, non-informative. That's the gray dashed line. And that's the posterior we got for survival rate using the two chain, the two like blue and red line. Okay, so you see here that our prior was really non-informative. Imagine now that we can include in the model some info. So there is this study on 27 European passerines, and they are using allometric rules. They can predict this. They show that there is a relation between survival and body mass, average body mass for one species for this 27 species. So if you actually know the body mass of one of the species, you can predict its average survival rate. So for deepers, average body mass is 59.8 grams. So from this study, we would predict survival rate should be around 0.57 with a standard deviation 0.073. So what happens in our model if we use this as prior information in the model? So instead of assuming a prior beta 1, or uniform between 0 and 1 for survival, now we're going to say that the prior for survival is a normal distribution centered on with mean 0.57 and standard deviation of 0.073. Actually, when we do this in the model as it is, we get the same mean value for the posterior for survival, but the credible interval, so how was it? What was it before? It was 0.52, 0.62, and now we get 0.52, 0.61. So actually, when we include this prior info in the model as it is, it doesn't change anything on our estimates for survival rates. So if we have enough data, prior doesn't affect much the posterior distribution. Okay, it's not so important. It doesn't bring more information to estimate survival rates. There is no increase of precision here, and mean value of the posterior is the same than before. But imagine now that we just had 3 years of data instead of the 6 years that we have. So we would have less individuals. What happened when we use prior info? Now, if we don't use prior info, so if we use a vague prior, now we get credible interval from a much less precise than when we had more data. And when we use a vague prior, it's very imprecise. But when we include prior information, there is a gain in precision that we didn't observe when we had the 7 years of data. Okay, so if we have a small data set, using information, including information in the prior, is going to help to increase the precision in our estimates. Okay, here 120% gain in precision. The mean value didn't change so much, but the precision is much better if we include prior information. So it's illustrated here. The red curve is the posterior distribution of survival rate when we include prior information, and the gray shaded area, the posterior without including prior information in the model. So we can see that there is really a gain in precision. Yes, the posterior is the variance of the posterior is much lower when we use prior information. So what we did here is including prior information using a normal distribution, but it's not really a satisfying way of doing it for several reasons. One is that if we use a normal distribution on survival, if we back transform, actually we use a normal distribution on the logit transform survival, but if we back transform using the inverse logit relationship, we'll see that it's like looking at the bathtub function. So it's giving more weights to some extreme values of on the natural scale of the survival. And the other issue that is very basic is that imagine if the prior would be near 0.9, there would be a risk that we draw some values that are above 1, whether survival can actually not, he's bounded between 0 and 1. So it's better to use the beta distribution to on priors for survival. And it has 2 parameters, alpha and beta. So they're both involved and related to the expectation of the distribution and the variance. Okay, I don't have time to go through it in details, but that's the parameters of the beta distribution. And we can, using some equations that are here, we can, if we want a mean value centered on 0.57 and a variance of 0.073 square, if we're talking about the variance, we can actually choose the alpha and beta value of the beta distribution to have a mean of 0.7 and this variance. Okay, so you have this code in the live demo number 5, so that you can set the parameters of your beta distribution to match your prior info. So here, for the European passerine, it would correspond to a beta distribution with alpha parameters equal to 25 and beta parameters equal to 19.34, blah, blah. So if we use this beta distribution as a prior in our model, it's actually the good way to do it. Okay, that would be the equivalent of this prior using the normal distribution. Maybe we'll get back to this issue of setting the prior in another class later. Okay, so sorry if I was not very clear here. So we also want to check that the prior that we set, what's the influence of the prior that we set in our model on the posterior distribution. So for this, we could do prior predictive check. But I don't think we're gonna see that in details today, but we just have to think of the priors that we set in our model so that it's reasonable. For example, if we would use a prior with a huge variance here on 1,000 square, it's compared to, which is really in a different scale compared to the variable that we use in the model. So we have to choose values of variance that are reasonable and comparable to the scale of the variables that we have in the model. So here, a variance of 0.5 square would make more sense than that would be 1,000 square would be very huge compared to the variable measured in the model. Okay, so keep reasonable priors, even for if you don't want to include prior information. And that's the bathtub shape I was talking about before. So if we use a normal distribution to set a prior on logit of survival, and we look at how this translates on the natural scale, so survival rate, when we back transform the logit, it's actually not so much non-informative. You can see that there is more probability of picking some extreme values near 0 or near close to 1. That's why it's better to use a beta distribution than a normal distribution when you set priors on survival rates. So if we choose a prior with a different variance, which actually would be a beta distribution, that would be an uninformative prior. Actually, you can see that the probability of choosing values from 0 to 1 is more equivalent, rather than very extreme here. Finally, let me just go back on the assumptions that are behind the capture-recapture model. We assume that there is not loss of mark, that identity of individuals can be recorded without errors. So typically when we read bird rings, we assume that we're not making errors here. And that individuals captures are random samples. So they are independent from each other. So typically this doesn't work for social species or group living species, because if you capture one, then the independence is not always respected. There exist other more complex models that would help to relieve some of these assumptions, but here we just use the yeah, the basic CGIS model that rely on these assumptions. We assume that there is homogeneity of survival and recapture probability among all individuals, except that have the same value of the covariates, that they're independent, so there is no over-dispersion in the model. We can actually test the validity of these assumptions using goodness of fit tests in particular that are specific to capture-recapture model. And there is now R package that is called R2UCare that has been developed by Olivier that allow you to test the validity of these assumptions within R. So it's really handy to use. It's really nice. And we can also use posterior predictive checks to evaluate the capacity of our model to reproduce our data. So that is another way of trying to test the goodness, to evaluate the fit of your model to your data. Okay, so you can look at the paper from Gelman in particular, because I don't think, we're not gonna cover posterior predictive check today. Finally, a few words about some identifiability issue that we might encounter sometimes. So I've talked about it briefly yesterday when we were going through the model with time-dependent survival and detection rates. We had a very low, forgot the name again, effective sample size for the last survival and last detection parameter. And it's actually a problem of identifiability that we know about that exists in the model with time-dependent survival and detection rate, that the last survival and detection parameter for the last sampling occasion, they're actually not, they cannot be estimated separately, okay? It's a structural problem in this model. I mean, it's not a problem, it's a structural thing. And if we look at the likelihood profile here, and imagine that it's the algorithm picking different values for the last survival, the survival over the last time interval. So whether we would pick 0.41, 0.52, 0.7 or 0.8, and look at the deviance of the model, which is related to the likelihood, we see that it's for these 3 different values here, it doesn't change much, okay? And that's showing us that there is a parameter redundancy issue. There is a non-identifiability of this parameter in the model. So when you have identifiability issue in the model, it appears in the trace plot because you'd see bad mixing for this parameter and in effective sample size that is low. And R hat can also be big, but not always. So the message here is that you should always check the mixing of your chains for each parameter and look at effective sample size, which should be high enough. Okay. Another diagnostic that is interesting is to look at your prior and versus your posterior distribution. If a parameter is estimated correctly, you should have something like this, the plot on the left with an informative prior here and very few overlap between the prior and the posterior. So you see a nice posterior distribution that is very different from the prior. Here on the graph on the right, it's more ugly, I would say. So the prior is more confounded with the posterior, so there is more overlap in between the two. And here the posterior distribution is not unimodal, is very wide. So we don't like that. We don't want that. So, or either run the model longer or make sure that you're not using a model that is too complex with regard to the data you have at hand. Another example here, we like that. Good situation, nice posterior distribution, prior is very different. Graph on the right, we don't like that. Okay, posterior is wide. The overlap with the prior is higher, about 40%. So you might want to run the model longer or make sure this parameter is identifiable. You don't have identifiability issue because it looks like you have. And a very important point to finish with, when we talk about survival in this Comarch-Jolly-Sieber, we actually means survival within the study area, so apparent survival. We assume that individuals remain in the study area here, so that mortality and permanent immigration are confounded. If some individuals have left the study area during the study, using this model that we just used yesterday and today, we would confound the two. Okay, so we are estimating apparent survival, not true survival. And apparent survival is the result of true survival within the study area times fidelity to the study area. And we're going to see today how we can use different models to overcome this issue. So always keep in mind that survival that you estimate here is probably a bit lower than true survival of the species, except for very territorial or philopatric studies. So always use caution with interpretation, and the best would be to combine with dead recovery data or use more complex model, spatially explicit or multi-state, etc. And that's some more references about CGS state space models, how to deal with missing values when we want to include the individual and time varying covariate, the different methods of imputation you can use, how to include prior information is in McCarthy and Master, how to combine live recapture with dead recovery data, spatial info, and one paper about identifiability issue in a Bayesian framework and how to recognize it and deal with it. Okay, that's it for me. I'm gonna stop sharing my screen. So I'm gone 15 minutes, 20 minutes more than time schedule. So I don't know, Olivier, how long you want to have a break?
No,
How
you're
long?
perfect. It's perfectly fine actually. You were supposed to finish at 10:30.
Oh, I had 1.5 hours. Oh, sorry, I really rushed into it. Oh, I'm sorry. I hope people could follow me.
No
I'm really
problem, no
not a
problem.
morning person. Sorry.
He's the morning person. Anyway, so yeah, I don't know if maybe we can have a chat on if there are questions on the Slack that need our attention
Yeah,
or
yeah. Probably I was not so clear on several points because I was trying to go quick.
I
Ah,
don't know.
okay.
I
So
thought
someone. Oh, Mathieu, but you're nice, Mathieu. Thank you. Ay, ay, ay.
I don't know. Is there anything you'd like Sarah to go over
If you
again?
want, I can go through the live demo a bit, like the model with random effect, because I know some people have asked about it yesterday. So
Yeah, apparently
okay,
that's
let's do it.
something.
So
Yeah,
I have 10 minutes, right? I'm really sorry.
9 minutes.
Okay, Olivier, you can scream when I should be done. Yeah, yeah, yeah. Tac, tac, tac. So, well, let's do the individual covariate then. Probably that's a good idea. How to add? Maybe I even have the model with sex. Tac, tac, tac. wing length. Okay, we can do the one with sex, maybe. The two ways so that people can see how using the nested indexing thing. Okay, tack. So first I have a look at the covariate sex. So I use the if-else function so to recode it as a 0 and 1 here. So if sex is M for male, I use 0, otherwise 1 for female. So we first write the model using this 0 and 1 covariate, so not using the nested indexing. Phi sex. So here, observation matrix and prior for detection is constant. Okay. I want to explore the effect of sex on survival. So I loop over each individual for the transition matrix. Logit of phi is equal to beta 1 plus beta 2 times sex of individual I. Transition matrix is indexed by I, okay, and phi is indexed with I2. Okay, that's good. Close the loop on individual. Provide priors for the regression coefficients using normal distributions. Here I can use normal instead of beta distribution because this is not a prior on survival, okay? This is a prior on regression coefficients, so it's fine. If I would use, if I wanted to provide a prior directly for survival, imagine we just had an intercept here and no effect of sex, so beta 1 would correspond to the prior for phi, then it would be better to use a beta distribution. But here it's fine to use normal distribution. Then we need to, so prior for beta 1 and beta 2. Then we want to keep track of male survival. So inverse logit of parameter beta 1 for males. And for female survival, it's going to be inverse logit function of beta 1 plus beta 2. Because for female, the variable sex takes the value of 1, so that female survival is going to be beta 1 plus beta 2 times 1. Then we define the likelihood, and we do not forget to index by individual here, so I, but not for omega. Okay, so we run this model. I mean, we just not run it, but load it. We run the command so that we define it in R. Then we can specify our constant, number of individuals, time occasions, encounter at first capture occasion, and we need to provide here our sex covariate. Okay, I can look at our constants to make sure there's no problem. Okay, sex, first encounter, number of individuals, number of time occasions. Perfect. Then we provide the data. So the data here is just the encounter histories, the capture-recapture histories. The covariate enters in the constant here, okay? And as before, we add 1 to the capture histories, but you don't have to do this if you do not use the dcat function. Here we use it in the likelihood here, so that's why we add 1 to each observation to avoid having zeros, okay? Because this function doesn't like it. Then we can set up the initial values for beta. We draw two values from normal distribution between, okay, with mean 0, variance 1. Detection, we draw one value from a uniform distribution between 0 and 1, and we keep the same initial values for the states, which is assuming that everyone is alive all the time. Okay, just have a look. Oh, no, I did not run it actually. Oh no, that's the function, sorry. Whew. Let me check. Yeah, okay, that's not doing it here. Which parameters to monitor? So beta, P, and phi for male, phi for male and female, because we want to know directly survival that we could recover from back transforming the beta, but it's good to directly be able to look at the posterior for survival of males and females. Okay, I set up number of iterations to 2000. That's maybe a bit low, but I wanted to go to run quick. So let's try with this and see if it's enough to converge. So the model should be phi depending on sex. Okay, my constant data. But did I define? No, so I didn't. Twitter. Sorry, I'm just checking. Okay, no, it's fine. So let's try and run this model now. Okay. Tuk, tuk, tuk. Should be quick. Just in the meantime that it's running, I just wanted to show you the other possibility to include sex would be to recode it as 1 and 2 instead of 0 and 1, and use the nested indexing. So phi would not be on the logit scale, but directly on the natural scale as a function of beta sex I within the brackets. So that if sex is 1 for male, phi equal beta 1, and sex takes a value of 2 for females, so it's going to be beta 2 for females. Okay, and this way, in the parameters we monitor, we just monitor beta and p, and beta 1 is going to be male survival, and beta 2 is going to be female survival. Okay, so that's the trick to for lazy people. Okay, so the model here is almost finished. It's almost finished running. So we can just have a look at the summary, and then I'll probably let you go because it's 10:30. Okay, let's have a look. With this first formulation, we have regression parameters beta 1 and beta 2, detection probability 0.9, female survival and male survival. Okay, so we're most interested in these 3 parameters, but also we're gonna use these 2 if we want to draw the prediction line. So the R hat are fine, so it actually seemed to be enough to converge. Effective sample size 2, so we would actually need to look at the, I can just do this and then stop there. Just have a look at the trace for, let's say, female survival and see how it looks like. Tac. Hop. So model is phi, sex, p, and parameters, let's say phi for female. Tac. Oh, it's very nice. Yeah, very nice. It's not bad, let's say. Mixing is good. Posterior is pretty nice. So all good. Okay, I'm done here. I hope it was okay.
Great. Okay,
Maybe.
so yeah, we can have a break for half an hour. That was the plan. Perfect timing. And so we group at 11 a.m. in half an hour. Okay, for the next lecture. See you in half an hour. Okay, we're back. So the next lecture is about estimating transition between states, and Chloe, yeah, okay.
I just had to stuff some last minute chocolate in so I can get through this.
Okay,
But
you
this
have the
won't be
floor.
so bad to get through because this is where things really get fun now.
Yeah.
Because
Okay, so
I actually had to come up to my first postdoc position to actually genuinely have to do a Cormac-Jolly zebra model. Before that, it was all multi-states models. So for many real life applications, we'll end up using one form or another of multi-state models because they're just very useful to capture the complexity of biological systems. So I'm going to share my screen now and take you through multi-state models. Yeah. Okay, is that on?
yes, it is.
Perfect. So let's get started. Let's get on the move with the estimation of transition probabilities. So a long time ago, and I think if we're talking about 1973, nobody's going to be offended if I say this was a long time ago. People suddenly realized that animals actually move around, and if you're tagged animals move around and you don't just capture them in a single location, but in several ones, you cannot just estimate survival, but you can also estimate the rates at which these animals move between different locations. And that is true both if your animals move around and are still alive, but also if your animals move around and then they're dead. So tag recovery started with fish first and with birds a bit later, when people found that you can ring a bird in one place or tag a fish in one place. And if it then gets shot or fished or killed in some other way, people can find it and the tag will still be there, providing information about both survival and mortality, but also about the movement that this individual made throughout its lifetime. So all of that work actually came from, all of that early work came from Canada. So thank you, Canada, and thanks the rest of the world for all of the amazing work that has been done on multi-state models between then and now. So essentially what we're doing now is we're making our models quite literally bigger and better and stronger and a bit more complicated, but actually a lot more useful as well. So let's get into that. And as you will see as we go through this is not just about animals moving between locations. It's about a lot of other things as well. It's about life history stages. It's about breeding proportion. It's about being alive and being dead. But we'll get into the different applications a bit more afterwards. And it would also be quite interesting to hear from you at a later stage, maybe what kind of models you are working with. Okay, let's do geese because people love geese, right? So these are Canada geese. And we're going to look at an example study that looked at the wintering site fidelity. So how likely these birds are to winter in the same location year after year. So there are 3 wintering sites that people looked at. And there was an amazing number of banded geese. So there was some 21,277 banded geese, which is really a quite amazing data set. So if we look at the capture histories that we see here, Like, let's take this individual here, for example. So this individual was first encountered in 1985 in location number 3. Then it was not encountered for the 2 next years, then encountered again in the same location 3. And in the last year, 1989, it was encountered in location 2. And we can definitely already see from the raw data that this individual has moved locations at some point during its life. And I mean, more specifically, sometime between 1988 and 89. So for the moment, we're going to forget about the 3rd location. To start with, we're just going to focus on there being 2 different locations. So unlike the Cormack-Jolly-Sieber model that we talked about before, where animals could be only alive or dead, animals can now be alive in one location, we call it site A, alive in another location, which is site B, or they can still be dead. If we start from the data that I just showed you, there are 3 things that can happen in that data. Number 1, we can have a non-detection or a 0 in that data. What does that, but let's not start with the non-detection because that's actually the tricky one. Let's start with a detection in site A. Whenever we have a detection in site A, we know for a fact that this animal was alive and in site A. Analogously, when we have a detection in site B, we know the animal was alive and it was in site B. So what about the non-detection now? Well, if we don't detect the animal, we basically know nothing about it. So that animal may have been alive in site A, but not captured. It may have been alive in site B and not captured, or it may have been dead. When we construct our models, we start from the other side. When we construct our models, we start from the state process first. So we start from the true state of the individuals. So if an individual is alive inside, if an individual is dead, again, let's start with the easy one. In this model now, we're assuming that a dead individual cannot be detected. Then, if we have an individual that is alive inside A, it can either be detected inside A if we capture it or recite it, or it cannot be detected. And the same is the case for an individual that is alive inside B. So could be detected inside B or could be not detected at all. That brings us to the 2 most important things when we work with multi-state models, and that is the transition matrix and the observation matrix. We'll start with the transition matrix. So first, the way you read this. So each row in this matrix represents an origin state, or I sometimes call it a from state as well. So this is the state at time t-1 here. And you can see the first row corresponds to state 1, which in this case is actually the dead state. The second row corresponds to state 2, which is alive inside A. No, sorry, now I'm mixing it up. Okay, it's going to switch around. Okay, so the first state is alive inside A. The second state is alive inside B. And the third state is dead. And then we have the rows. And the rows, no, sorry, I'm all confused today. And the columns, there we go. The columns are the destination states. So they are the states at the next time step, here time t. And again, we have the 1, 2, and 3. So if we go through the first row together, this first element is going to represent the probability of an individual that is currently in state 1 to be in state 1 again at the next time step. Then the next entry is the probability of an individual that is now in state 1 to be in state 2 at the next time step. And the third one is the probability of an individual now in state 1 to be in state 3 at the next time step. Now we can see there's two types of letters appearing here. We have the phi's that we are already familiar with. So the phi's are the survival probabilities. So we can see here we have phi A, which is the probability of an individual inside A to survive to the next time step. And then we have this psi, and the psi represents transition probabilities. And the way we write it now, it's quite easy. This psi AB is the probability to transition from site A to site B. So if we look at this middle element here, this is the probability of an individual in state 1 to be in state 2 at the next time step. And in order for that to happen, this individual first needs to survive, and then it needs to move from site A, where it was last observed, to site B, where it is next observed. Similarly, if we have an individual that remains in the same location again, it needs to survive, and then it needs to not move to site B, which we here represent by 1 minus the probability of going to site B. And finally, just like in the Cormack-Jolly-Sieber model, if it becomes dead, that's 1 minus the probability of survival. And also, like before, the dead state only has a single option, and that is to remain dead, at least as long as there are no zombie geese. Okay, so that's the transition matrix. Next, we have the observation matrix. So here, the interpretations of the rows and columns are a little bit different. So the rows, again, are the states, the latent states. So again, we have number 1, alive in site A, number 2, alive in site B, and number 3, dead. The rows, the columns now represent the observations. We have a non-detection at 0. We have a detection inside A, and we have a detection inside B. So when we read this now, again, we go through the first row together, and we start in the middle because it's easy. So the probability of detecting an individual that is alive inside A as inside A is this probability of detection inside A. Then the probability of non-detection is 1 minus the probability of detection. And we assume that we never detect an individual that is inside A, inside B. I would also like to point out that there's an error here. So this should say B, because obviously we should not be detecting an individual that is inside B with the observation probability for site A. Okay, so we have a transition matrix and we have an observation matrix, and these are really essential. So whenever you start working with a multi-state Mark-recapture model, it's always best to write these matrices out as early as possible. Either do it on paper or print it out so you can always keep it with you, because you will go back to look at that a lot. So how you code your states and your observations is entirely up to you. So we could just recode this and say that the non-detection is 3 instead of 0 and move things around. But at the end of the day, the most important thing is no matter how you code your state and observations, you have to make sure that you can always keep track of it. Best practice, how to make sure you can always keep track of it in addition to just having your matrices printed out. At the beginning of your model code, just write it down. Like, believe me, it's worth it. Just write down what your states are and how they are coded and what your observations are. So you see that we've now made a slight change here. So in the observations, we are now coding the number 1 as not seen or not observed, the number 2 as seen inside A, and the number 3 as seen inside B. The reason for that is that we cannot use 0 in the categorical distribution as we've seen yesterday for the Cormack-Chilli-Sieber model as well. But as long as we have it written out in the beginning of our code and we have our matrices next to us, this is going to be fine because we can keep track of it. Okay, so let's go into how we write it in the model. First, let's start with the priors, and we want the priors for all of the parameters that matter. So at the top, we have the survival probabilities that are now specific to the sites. So we have survival probability inside A and survival probability inside B. Next, we have the transition probabilities, where we have a probability to go from A to B and a probability to go from B to A. And keep in mind that we don't need to provide a prior for the probability of remaining in a site, because that's simply the probability, it's simply 1 minus the probability of moving. And finally, we have the recapture rates, again for site A and site B. And for now, these are all uniform priors, 0 to 1. Next, we need to deal with the probabilities of initial states. And we've talked about this in the context of the Cormack-Chilli-Sieber model a bit again already. So we can assign specific probabilities here to represent the probability of being in a given state at the first capture. But actually, for now, we assume that we do know the initial state, because if we capture an individual for the first time inside A and we mark it there, we know it was inside A at marking. So instead of using these different probabilities for the first state, we can just set the first state to the state we have observed. Now, there is this funny -1 here, and that's basically here because of the way we have defined the states, and that will make more sense when we work through the coding tutorial together. And as said before, this also applies to the Cormack-Chilli-Sieber model. Okay, next, it's the return of what? Yes, your transition matrix. Transition matrix comes back. And we write it exactly the same way. And now it becomes very handy when you write that to have your printed out copy of your matrix next to you. So here we always have the first index is the from state or origin state. And the second index is the to state or destination state. So this first entry is the probability of remaining in state 1, given that you are in state 1. The next one is the probability of moving from state 1 to 2. And the last one is the probability of moving from state 1 to 3, also called dying in this particular model. And you see that these products here are exactly the same ones that appeared in the transition matrix earlier. The same applies to the observation matrix. So again, we read it as the first index is the observation and the second index is the state. So the probability of observing an individual in state 1 as an individual in observation 1 is, which observation 1 is non-detection, is a 1 minus the probability of observing it. So here it's really important that you keep track of how you log things. And you can see here we have some excessive commenting here as well, but it's really, really important. And it really, really helps you if you write these things down, because it allows you to keep track. Multi-state models are all about bookkeeping. Then we move to the likelihood. And the likelihood is very, very similar to what we've been using so far for the Cormack-Jolly-Sieber model. So note first here we assign the state at first capture. And then we go into the likelihood for the capture histories. So first, we have the likelihood for the latent state. And again, we have our categorical distribution here. The thing that's important now is that we're going to need the correct index here now, because we need to make sure that the transition probabilities we use in the categorical distribution correspond to the state that the individual was actually in at the last time step. Because we have the current state here, and from the gamma, which is our transition matrix, we now take those entries that are relevant to the previous state of this individual. And then we use the whole range that is available. It works the same for the observation. So here we have the observation, and the observation is conditional on the state. Note that for the observation process, the time index is the same because we observe an individual based on the state it's currently in. But for the transition process, the transition is dependent on the state the individual was last in. So if we run this kind of model, we get out more parameters now than we did before. But you can see they all appear here on the top. Recapture probabilities, followed by survival probabilities, and finally transition probabilities. We can also visualize those together and have a look at what kind of estimates we get, how they relate to each other, and what degree of uncertainty we have in them. Although one could argue that it does not make a lot of sense to compare recapture probabilities to transition probabilities. So let's go back to those geese. Remember, there were actually 3 wintering sites, not just 2. So what do we do with that? So the transition probabilities are still probabilities, which means each and every one of them has to be a value between 0 and 1. However, in addition now, we have 3 transition probabilities and they need to sum to 1. Because any single individual cannot, it only has a worth of 1. So unless individuals duplicate as they move, the sum of the transition probabilities from any given state has to be 1. So there's two ways to deal with this when we have 3 or more sites. And the first one is using a Dirichlet Prior, and the second one is using a multinomial logic link. Let's look at the Dirichlet Prior first. So the Dirichlet Prior is a prior that takes 3 different parameter values. And here you can see, depending on how you choose these values, we get different numbers out of it. In the top left panel, you can see the Dirichlet distribution with the 3 times 1 as the parameters, and that's essentially non-informative. You can see it spans the whole range from 0 to 1 for any given for any given parameter. And then if you look at the other graphs, you can see the higher a number we put in here, the more narrow becomes the distribution. So if you want to include any prior information into something like this, it's always good to simulate it first and see what it looks like. In Nimble, we have the Dirichlet Prior has its own distribution call here, and we just add this alpha with values 1, 2, 3. So this alpha, we pass it as constants in this case. Now, transition matrices. So this transition matrix is bigger now, you can see, because we have an additional state. So we now have individuals in state 1, which are in site A, in state 2, which are in site B, in state 3, which are in site C, and still state 4, which is now dead. But it works the same. And again, the useful thing to do is write it down as the matrix first, and it will make it much easier to transform it when you write it into your model. And again, when we run that, numbers come out, and we will look at the numbers a bit more during the coding tutorial. So the second option, in addition, or instead of using the Dirichlet Prior, is we can use the multinomial logic link function. So let's assume we have a number P sites or states. So what we do is we specify a normal prior distribution for P-1 transition parameters. And these can now be made functions of covariates, or we can add random effects to them, or different types of constraints. Then we back transform them using this formula, which is the formula for the multinomial logic link. And that makes sure that all of them will be between 0 and 1, and that their sum is less than 1. Finally, we calculate the last parameter as 1 minus all of the others. So this is the Nimble implementation of the multinomial logic, so not Dirichlet Prior here. And you can see that here we now have these normal priors on the transition probabilities. And we have that for 2, because we have 3 probabilities in total. Then here we have the formula for the multinomial logic link. And then in the final step, we calculate the last probability as 1 minus the other 2. So this is exactly identical to what I showed before. And numbers again we will look at more in a live demo, which we are quickly going to go through together now. So I will stop sharing this one. And we will move over to our studio. Okay, did that come up?
Yes.
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 Right. So packages first, and then we're going to load in this Goose data. And we're going to format it as a matrix, and then we can have a look at it. So this is exactly what we saw on the slide earlier. It's this Goose data that has observations coded as 0, which are not observed, 1s, 2s, and 3s. So first, again, we'll do the model that only has 2 sites. So we'll make a copy of our capture histories, and then we will set all the observations in site 3 to 0. So we basically pretend that there were no detections in site number 3. Okay, so out of this, we get the new capture history matrix, which now only contains 0s, 1s, and 2s. Next, we extract the first capture location for each individual. And then we proceed to write the model. So you see here, most important chunk of the model, your bookkeeping. Then we have the priors for the different probabilities. Again, as a reminder, now we only have 2 transitions, so we don't actually need a multinomial logic or a Dirichlet distribution yet. Then this is the transition matrix and the observation matrix. And finally, the likelihood. So we're collecting all of the data. And so here, I remind you now, you see our capture histories at the moment contain 0s. And as we heard many times already, we cannot pass 0s to the categorical distribution. It's very obvious why now, because here we add the state. If this is 0, then the index becomes 0, and that makes no sense. So we need to get rid of these 0s, and the way we do it in this particular case is just by adding +1. But it means that all the 2s become 3s, and all the 1s become 2s, and the non-detections become 1. Again, bookkeeping. Then we add the constants. So here we have the first occasions for each individual. We have the number of years and the number of individuals. Again, we need to set initial values. So it's not quite as easy now as it was before. So for the initial values, we again, whenever we have observations, we use the corresponding states. And in all other cases, we just add either state 1 or 2, which is either one of our alive states. The important thing to keep in mind when you work with multi-state models now is when you generate your initial values, it's possible that in your specific model, there are impossible transitions. So, for example, it may be impossible for birds to move from site A to site C, just because those sites are too far apart, for example. Or it makes more sense a bit later when we talk about life history stages, where an adult, for example, cannot go back to being a juvenile. And this you have to take into account when you simulate your initial values. You cannot simulate or you cannot pass impossible initial values. So this again, it's about bookkeeping, and it's about keeping track of what's possible and what's not possible. It's a pain in the ass, to be frank, and especially if you have complex model, it can be quite intensive to figure out how to do that. But it also helps you understand what's possible and what's not by going through it. And I'm going to put a little teaser for Perry's lecture this afternoon. When we talk about marginalized likelihoods, we can actually completely drop the latent state for the initial values, and we don't have to worry about this ever again. But for today and for right now, we have to worry about it. We set the parameters that we want to save and the MCMC settings. I'm going to jump down a little bit now, because this first model that we run here actually is the one where we sample the initial state probabilities. But we saw during the lecture that we actually know these. So in the interest of time, I'm going to skip ahead over that. And I'm instead going to run this next one, where we set the initial state probabilities to what we have observed. But feel free to run both of them later and actually have a look at the convergence diagnostics of the two different runs. So I'm on my small laptop here, so this is probably going to take a moment. But I think while this runs, we're actually going to continue with the lecture, and we'll get back to this later. So, where did my Zoom go here? So going to move back to the lecture slides now. Because this is where things get interesting now. So far, we only talked about sites as in locations, but sites may be states, and states can be an awful lot of things. And they can be extremely useful when we study biological processes. So here are some examples for things that we can run multi-state models for. For example, our states represent different epidemiological or disease states, such as sick and healthy, or uninfected, infected, and recovered individuals. Or it can be related to morphology. We touched upon this briefly earlier with Sarah, that, for example, we can categorize individuals as small, medium, or big, or light, medium, or heavy. They can be breeding states. For example, we can look at breeders or non-breeders. We can also look at failed breeders and first-time breeders. They can be much more generally life history states. For example, if we have animal populations where individuals can be in juvenile, subadult, and adult stages. They can be social states, when we make a distinction between solitary and group living individuals, or perhaps subordinate and dominant ones. They can be death states, so we can categorize individuals as being either alive or dead from different causes, for example, dead due to harvest or dead due to natural causes. When it comes down to it, the state is essentially an individual, time-specific, categorical covariate, which is quite a mouthful, but it's essentially what we need to work with biological processes the way they are out in the wild. And it's important to say that these examples above, they can also be combined. It's basically up to you and your study system what is appropriate. Let's do more birds. So we move from geese to seabirds, and specifically to this sooty shearwater. I don't have cool bird facts. I bet most of you know more about cool birds facts than I do, so I'm happy to read them afterwards if anybody has stories about this particular bird. So what people studied in these birds was life history trade-offs. So some data was collected between 1940 and 1957, and that was then analyzed using multi-state models in 2001. That's also where we got this data from for the demonstration today. So when data were collected, there were 4 states that were considered. So there was alive breeders. There were birds that were accompanied by another bird in a burrow. There were birds that were alone in a burrow, and that were birds that were captured on the surface. And obviously, the dead state is always part of this. For the example we're going to look at, we're going to pool this data, and we're just going to look at breeders, non-breeders, and dead individuals. So that means that what we call a non-breeder in this particular state includes failed breeders, so birds that have bred previously but aren't breeding at the moment, and pre-breeders, so birds that have not yet bred in their life. Okay, so the states we're going to be talking about is the B state, which are successful breeders, and the NB state, which are non-breeders and pre-breeders and failed breeders together. From now on, I'm just going to say non-breeders for simplicity. The types of observations that we have are non-detections, detections as breeders, and detections as non-breeders. And the questions that are interesting to look at here, for example, is does breeding or not breeding affect survival? Or maybe does breeding in this year affect the probability of breeding in the next year? So to what degree does breeding trade off both across time and with survival? Let's have a look at the data. So again, we have capture histories that have 3 different types of observations here. We have the ones, which, let me quickly check. Yes, the ones which are breeders. So this bird was first caught as a breeder. And then for the next 3 years, it was caught as a non-breeder. And then it wasn't seen anymore. So again, we do a transition matrix. And this transition matrix it has exactly the same structure as the last one we looked at. Just the interpretation of the parameters is different now. So for a breeder here, its probability of being a breeder again in the next year is the product of the probability of surviving and not transitioning to the non-breeding stage. For this bird to be re-encountered as a non-breeder, it needs to survive and then transition into the non-breeder stage. And finally, for that bird to end up dead, it needs to not survive. Again, the probabilities of remaining in the same stage, they aren't explicitly included in the model because they are just 1 minus the probability of transitioning. Then we have the observation matrix. So again, we have zeros or the non-detections, 1 are the detection as breeders and 2 are the detection as non-breeders. And it's exactly equivalent to what we saw with the sites earlier in this lecture. Okay, let's get into the model. So again, the first thing we do is we do our bookkeeping. We write down what our parameters mean, and most importantly, we write down how we code our states and our observations. Then we go into the model code, and again, we set the priors. For this example, we use uniform 0 to 1 priors for all the parameters again. Then we write out the transition matrix, and we write out the observation matrix. We also write exactly what we're looking at so that we can make sure we are not mixing things up. Finally, we specify the likelihood. And again, this is identical to before. The fantastic thing is that with any multi-state model, it doesn't matter how many states you add or what your states mean. The likelihood stays the same. The only thing that changes is this number range here. Like if you have more states or observations, you will have to adjust this number. But otherwise, as long as you call your observation matrix gamma, your transition matrix gamma and your observation matrix omega, you can use this exactly same snippet of code for any multi-state mark recapture model that you're using. Okay, so again, if we run this model, we get the estimates for all the different parameters, and we can look at them together. So, like I already mentioned before, when I showed you some of the examples of what states can be, we can do a lot using multi-state models. We can look at a variety of biological processes, including, for example, access to reproduction, temporary immigration, which is when individuals can leave the study site area and then return, or they can be unavailable for capture for some other reason. For example, if we have species that hibernate, they will be temporarily unavailable whilst in hibernation. Or if we have individuals that just enter states that we cannot capture. And finally, we can also look at combinations of life and dead encounters. And that's particularly interesting for 2 things. One of them is estimation of true survival and emigration rate. And the other one is for studying cause-specific mortality. So individuals dying, for example, due to harvest and due to natural causes. So we're going to look at a few more transition matrices together, just so you can see a little bit more of what different applications look like. So this next one is about access to reproduction. So here we have juveniles as the first state. And then we have first year and second year individuals here and here, which may become breeders with a certain probability. And that's this breeding probability alpha, either alpha 1 for the 1-year-olds or alpha 2 for the 2-year-olds. And then we have breeding individuals that breed every year. And also the dead ones, of course. So let's go through another row again. So let's look at this juvenile individual. So the probability of the juvenile to be recaptured as a juvenile in the next year is 0. So that's important now, because that means we have what I mentioned earlier, we have an impossible transition here. So there's no way a juvenile is recaptured as a juvenile. This we need to keep in mind when we do the initial values for this model now, because our initial values should never contain 2 juveniles in a row. But if this juvenile survives, it can become a 1-year-old non-breeder. If it does not breed, so we have 1 minus the breeding probability here. There's no way the juvenile can become a 2-year-old because you cannot skip age. But this juvenile can also become a breeder, and this happens if it survives with the survival probability phi1, and then becomes a breeder according to the breeding probability alpha. And as always, there is non-survival as an option as well. If we look at the breeder instead, so that's the breeding stage here. This one, it cannot go back into any of the previous states, but it can remain a breeder if it survives, or it can die and enter the dead stage. Then we have the observation matrix that goes with that. So this is a model that is quite typical for seabirds, I believe, where usually it's impossible to detect the juveniles. So they are often ringed as chicks, but they cannot be captured while they're in the juvenile stage. Actually, no, sorry, these ones are probably not captured at all. But anyway, so we see that these juveniles have a probability of 1 for scoring in observation 0, which is a non-detection. For all of the other stages, they can be either detected with a probability p in the corresponding place, or not detected with the probability 1 minus p. Okay. What about if we're interested in temporary immigration? So again, think about species that either leave the study area, for example, and they are on a seasonal migration, or species that go into hibernation. So again, we have a first state, which is individuals inside the study site. Then we have the second stage, which are individuals outside the study area, and the dead state. And here I'm gonna make you look at the observation matrix first, because the way we define in and out, it can be geographically, as in actually inside or outside the study area, but it relates much more to actual catchability. So in means it's possible to catch this individual, and out means it's impossible to catch this individual even though it is alive. And we can observation matrix, where we see for the individuals that is inside, it can be captured with probability p or not with probability 1 minus p, but the individual that is outside can never be captured. So it looks exactly the same in the observation matrix as a dead individual does. The difference is in the transition matrix, insofar that an individual is out can come in again. So if we look at this out individual here, the probability that it re-enters the study area is the product of surviving and then re-entering the area. Similarly, it can remain outside the study area. Again, it needs to survive and then not re-enter. Finally, it can die again as well. Then, as a final example, we're going to look at the combination of life and dead encounters. So as I mentioned earlier, that's quite common for fish and birds, but more and more also for other species. So it happens when marked individuals can be found dead under different circumstances. So they may just be found dead haphazardly, so people may just stumble upon a carcass, or they may actually be harvested, so shot or fished by someone. Again, we consider 3 states. We have the alive state first, and then we have this just dead state or newly dead state, which is now different from dead for good. So unlike in the previous example with temporary emigration, where we had a difference between states only in the transition matrix, but not the observation matrix, we have the opposite situation here. Because in the transition matrix, it makes no difference whether you have just died or whether you have been dead for a while. Because no matter what happens, you're going to end up dead. However, in the observation matrix, there's a difference now, and that's the reason why we need to make a distinction between the just dead individuals and the dead for good individuals. The reason is that they have different probabilities of being observed. Specifically, the dead for good individual is still the same type of dead that we talked about until now. Basically, it's not observable. It will never be encountered. However, this very freshly dead individual, that's different now, because that can actually be encountered or observed. Specifically, it can be encountered as newly dead with a probability R. And we often call this R reporting rate. And it's essentially the probability that someone finds this individual and reports the tag on this individual. So it's usually a product, and in most cases, we cannot disentangle the probability of someone coming upon a carcass and the probability of actually reporting it. So there is both there is both an actual encounter process in there and a human reporting process. But in general, we call it the reporting rate. And again, with the probability of 1 minus the reporting rate, this newly dead individual will not be observed. So it functions the same as the recapture rate, but it's a different parameter. Okay, so in the beginning, we talked about this multi-state model being bigger and better in many ways. They give a lot of flexibility. It's possible to make them extremely complex if you so desire, but there's a downside to that, because not everything is always possible. And what's possible is dictated very much by 2 things, namely your data and the model structure. So here we do a small example with simulated data. So we have 2 sites or states and 7 occasions. We have a survival probability of 1 for this particular example, and a detection probability of 0.6. And then we have 2 transition probabilities between the states 1 and 2. So again, this data looks quite familiar now. We have a capture history that consists of 0s, 2s, and 1s. So if we look at the deviance of this is wiggly. And we talked a little discussion about wiggly on Slack yesterday, for those of you who saw it. There is harmless wiggly, which is what the case yesterday was about. But this is not so harmless wiggly, because we actually have a case here where it's possible that some initial values can lead to local minimums, and some other initial values can lead to global minimum. So this is a case where the type or the way we choose our initial values can actually affect the outcome. So if we look at the parameters, we can see here, if we look at the chain of detection probability looks fine. But the chains of the transition probabilities, there is some odd behavior here. Namely, we can see that there are 3 very distinct drops. 1, 2, 3. And this happens for both of them simultaneously. So something's not quite right here. If we look at the posterior distributions, again, we can see detection looks kind of fine, but now for the transition probabilities, now that's clearly a bimodal posterior. So we see that there are 2 maximum or like 2 points of high sample density in both of these. And that's a very clear case that's telling us, yeah, there's something that is confounded here, something that may be not identifiable. And that's when we need to look more into our model structure, the assumptions it makes, and what our data actually provides in terms of information. So that goes into the realm of advanced troubleshooting, and we're not going to go into too much more detail on this now, but just have some more references for further reading here. So the first one, that is the go-to reference or the initial Bible. And then towards the end of the course, Olivier will also share with us a much more comprehensive list with an overview over what people have actually been using multi-state models for ever since the Canadians invented them all the way to very, very recently. Okay, now we can go back to the demo, and I'm sure that model is run by now. Just give me a moment. Please excuse me for 2 minutes. The fire brigade is at our door and my boyfriend's Norwegian is not so good. So I'm just very quickly gonna have to run down and check what's going on there. I'll be right back.
No problem. Yeah, hope it's okay. Okay, so we can have a short break until Chloe is back. Yeah, we're supposed to finish at 9:30. Okay, so let's have a short break while Chloe is sorting out the file issue.
Okay, I'm back.
Oh, that was a short break.
Yes, no, my landlord was home after all. They want to
Everything
clean
is
the
okay?
Yes.
Yeah, okay.
Okay, so let's go back to the coding tutorial then. Here. Okay, is this back on?
Yes.
Okay, so we can see that this model has finished running a while ago, and we can have a look at the results. So let me just go up to, because it would be nice to have a look at the plot as well. So we have to remember now this was back with the model that has the sites. All right. So next is the application with the multinomial logic, but I'm gonna go ahead over this one now, so you can look into that one yourselves, because we looked at the important snippets of code during the lecture, which is essentially this part here. What happens a lot of the time is actually that at the end of the day, you will not need the Dirichlet distribution or the multinomial logic for your multi-state models, because quite often you end up with something like what we saw with the last few examples I showed you, where your transition parameters are actually, they have biological meaning. They are like breeding probabilities or cause-specific mortality rates or something like that. And you can actually express the elements of your transition matrices in terms of products of biologically relevant parameters that can be given simple uniform priors. But it's good to know how to deal with it in case you do end up with a model where you have multiple transition probabilities that need to be constrained to sum to one. Okay. Okay, so we're going to go through the example with the shearwaters now. So we're going to read in the data. And we have another look at this. We'll also look at the bottom of it, just so we see a little bit more. But remember, so we have capture histories again, where we have observations of ones, twos, and zeros. We go into our model code and we have a look what these observations mean. So we're going to be adding +1 to this matrix again as well, because we cannot deal with the 0. So in this resulting widen, all the number ones are non-observations, twos are seen as breeders, and threes are seen as non-breeders. And these correspond to the 3 states: alive as a breeder, alive as a non-breeder, and dead. The different states and observations are connected by 3 types of parameters: survival probabilities, transition probabilities, and recapture probabilities. Inside the model, we need to provide the priors. We need to specify the transition matrix. We need to specify the observation matrix. And then we reuse the same snippet of likelihood that we've been using in several others of our multi-state models. So let's run this. So we make the data. So you see here we add the +1 again. We extract the date at first capture. And on this occasion, I can maybe mention something that came up on the Slack a bit earlier. And that is that sometimes, especially when we work with large data sets where we have many, many observations for many, many years, especially when we have relatively many years of observation relative to the species lifespan, we sometimes don't just take the first observation, but we also get the last observation. Let's say you study an animal that has a lifespan of 3 or 4 years, but you have collected data for 50 years. It's a bit of a waste then to, like, in your likelihood, analyze the whole capture history from the first occasion to the end of the study period, because there is no way an individual that was marked in the second year is going to be still alive in the last year. So instead of having the K here, you can replace this by the last occasion of an individual, where you could, for example, say that if your species generally lives 3 to 4 years, you could just say the last occasion is going to be the last observation plus 10 years, which is very generous, but it will still save you quite some computation time if you basically don't analyze all those data points where you know this individual is going to be dead, because there is just no way for it to be alive. So we have the data, we're going to assemble the constants. Again, we need to make the initial values and make sure we only have possible transitions in our initial values. We set the parameters to monitor, MC specs. And you can see now, I talked about this briefly yesterday, we now don't use the thinning rate. At least we don't set it specifically, because we just want to use a thinning rate of 1, and it's going to default to that even if we do not provide it. And then we can run this. Hopefully that won't take too long. That's a very important part of working with Bayesian mark recapture models too. Figuring out what to do while you wait for your models to run. Because even with very efficient implementations, you sometimes end up waiting for quite a while. Especially if you're going to be testing out several different models and model structures. I think it can really be worth to learn how to use your local computing cluster to do this. Because if you need to sequentially run all the different versions of your model on your own machine, and it's clogging up all your memory all the time, that's really inconvenient. So I can say from experience that it's worth learning how to use the cluster if you're going to be spending a substantial amount of time running mark recapture models, or even bigger Bayesian models for that matter. I think I'm actually quickly going to move because they started cleaning the chimney like right next to me now. So I'll be right back.
Okay, so we can have a look to the model fitting on Chloe's computer while she's away. Almost done. It's very good advice from Chloe to try and maybe locate computer resources like clusters, or to if you have to run big models on big data sets. Yeah.
Okay, this should be a bit better now. Now the only sound you have to deal with besides me talking is the sound of this laptop taking off as it's finishing to run this model. But we're almost there now. Okay, there we go. So we can look at the summary as before, but the more parameters we are actually monitoring, the less informative the summary becomes. So plots are always better than tables. So here are the results visualized. And then we can go back to this question that we had in the beginning, which was about trade-offs, if you remember, about survival and reproduction. So we can do a comparison here. And essentially we plot two posterior distributions together. So this is the survival rate of the breeders in green and the survival rate of the non-breeders in purple. So the first thing that you can see here is that there clearly seems to be a survival cost of reproducing, since the breeders have substantially lower survival probability than the non-breeders. The second thing you see here is that those posteriors are a bit wobbly, wiggly, pointy. So we'd probably want to run that for a bit longer and probably with more chains if we wanted to publish this result. Okay. And that's basically the end of this tutorial here. So thanks for bearing with the fire brigade emergency and the laptop taking off noises. And I hope this was useful for you to get started with your own multi-state models. And I'm just going to say it one more time to be a little bit annoying, but write out your matrices and make sure you have that part in the beginning of your code where you write out for yourself how you define your states and be worth it. Okay, me out, I guess.
Yeah, so okay, that's the end of the morning session, and we meet again at 2 p.m. That was the plan, was it? Yes, 2 p.m. Okay, so for the next lecture on an extension of multi-state models to deal with uncertainty in the state assignment. So see you in 1.5 hours, roughly. Have a nice lunch break and see you.
I forgot something. For those of you who haven't filled out the survey yet, it's still pinned in the Slack general channel. And I'm going to put the link into the webinar chat box again too. So if you haven't done that yet, it would be really awesome if you could.
Do you copy and paste the survey link is in the webinar in the chat? Okay. 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 Have a nice lunch break and see you in 1.5 hours. See you guys.